Yes, ma'am.
See that narrow depletion region should be there. You have to know that while drawing the forward biasing, it should be narrow depletion region. Okay, so note down this should be connected to the forward biasing, positive to positive, negative to negative. Okay, so what was the final thing? The large current, forward current flows through the junction. Forward current crosses the junction. During forward bias, applied DC voltage, what we have applied DC voltage opposes the fictitious battery, the imaginary battery developed across the PN junction. This is the first point. The potential drop decreases. Potential drop decreases. What will happen? The diffusion of holes and electron increases. Depletion region thin. So it offers a low resistance. So you want to note down the characteristics of the forward biasing?
Yes, ma'am.
So the first one, during the forward biasing, so you remember that, isn't it? Forward biasing. The applied DC voltage opposes the fictitious battery developed across the PN junction. Due to this, the potential drop across the junction decreases. And as a result, the diffusion of holes and electrons across the junction increases. The depletion region is thin now. The depletion region is thin now. And junction diode offers a low resistance during the forward bias. So, shall we go to the reverse bias?
Yes, ma'am.
So what will happen in the reverse bias? P-type and P is connected to negative and N is connected to positive. This is the reverse biased. Free indicates the free electrons flow towards the positive. So these electrons from here starts flowing to the positive pole of the battery, positive terminal of the battery. The holes here, what will they do? They will go towards the negative terminal of the battery. So they have attracted the electrons here and the holes towards the negative terminal. So what will happen to that the junction? There are relatively few electrons and holes. The minority carrier only they will move. This point you have to note down. Even it is the minority drift current in this case, it is independent of the applied voltage. This we are going to see in the graph when we are going to see. This current is called as leakage current or reverse current. The circuit is set to reverse bias. What is minority carriers flow? Minority carriers, few electrons and holes, they try to cross each other. That's all. So what will happen? This reverse bias, no? This applied voltage, DC voltage, aids the 50 TS battery. Aids, which it helps the more. The 50 TS battery, the width becomes more. Due to this, the potential drop across the junction increases. So, wide depletion region. The barrier height will be applied voltage plus this. So, the height, the barrier height, the width increases. Do you follow? So, the potential drop across the junction increases. The diffusion of holes and the electron automatically decreases. So the depletion region is thick. Junction diode offers a high resistance. When you draw, you have to draw a bigger one.
Can you explain that leakage current again?
Which one, ma?
You said that leakage minority carriers are flowing.
Minority carrier, which is independent of the applied voltage. So at what voltage and that. Suddenly when it is there, the minority carriers, when it is reverse biased, automatically which is the minority carrier here? In the pole.
In P, the minority will be the
electrons.
Electrons.
The electrons start moving towards this positive. And holes from here will start moving very few. That is called as when the minority carriers are moving, when the minority carriers are crossing the junction, what it is called? Drift. This drift current is called as leakage current or reverse current.
Yes.
Now, shall I final summary as the previous one? Do you want to take that?
Ma'am, just can I try and explain it just to confirm if I've understood or not?
Yes.
So, from what I have understood, we took the normal PN junction diode, and this time instead of connecting positive to the positive to P, this time we're connecting negative to P. That is, we are connecting negative towards and positive towards N. So what is happening is the negative side of the battery is technically attracting the holes of the P junction.
Correct.
And similarly, the positive terminal of the battery is from the N side, it is attracting the electrons. Because those are the majority carriers for each of them. So now, because the majority carriers of each side have gone down, that will mean the depletion region has increased.
This, now, if we ask the formula, this is this. V naught plus. There it will be minus. Correct. Tell me.
So now that depletion region has increased, the we can say that the depletion region is somewhat resisting the potential of the battery.
Yes. Depletion region, or not the battery, depletion region increases and it suppresses the majority carrier flow. What is the majority carrier flow? Tell me what happens in the forward biasing. It suppresses that action. Can you tell me what happens?
Forward biasing, the holes move towards the
the holes moves towards the.
In forward biasing, the holes move towards N. And electrons move from
what is suppressed? The electron which is moving from N to P, and holes which are moving from P to N are suppressed here.
Yes, ma'am.
It is suppressed. Now, for that, what happened? The DC voltage which we are applying helps the fictitious battery developed across the junction, aids. So the potential drop increases, diffusion current, diffusion of holes and electron decreases. Depletion region is thick. If depletion is, it offers high resistance. It will not allow any current to pass. But independent of the applied voltage, there is some leakage of current called minority current. Is it clear? To draw this diagram and write this state, which is suppressed, then I will give few points you can note down. It will be helpful.
Just a doubt. Now that, so like the positive, okay, so the holes from the P side got attracted towards the negative terminal.
Yes.
And the electrons from inside went to the positive terminal.
Yeah.
And now the electrons from P side have gone to the N side due to minority charge.
Not all, minority, very few. Leakage current, we are going to take it as a negligible current, very small current. So I'm going to teach you the VI characteristics of the graph. That time I'll show it to you.
Yes, ma'am. But then now that so many ions are flowing, since there is so much splitting of the atoms present in the semiconductor, because we learned that the flow of these holes or electrons is when the atoms get excited and move to conduction band, right? So now that so much excitation is happening, how does the semiconductor not break down or something?
Wait, we will see. I'll explain to you now. This is the reverse biasing current, and when it crosses the barrier potential, see, we will see the graph now. First, you try to understand this. In the case free, you want to write this? Free electrons?
I've written this one.
The last paragraph have you written? Due to the reverse bias, applied DC voltage aids the fictitious battery. Have you written that?
Just a minute. I'm going to write that down.
During the reverse bias, applied DC voltage aids the fictitious battery developed across the junction.
Why is it called the fictitious current? Huh?
This one, this battery.
Yes, but then it's not fictitious, right? It is creating a potential.
Okay, creating, but it is given. Imaginary battery. Due to this, the potential drop across the junction increases. And as a result, the diffusion of holes and electrons across the junction decreases.
So the diffusion current is going down, but you said that the minority movement is less. So is it correct to say that the displacement current has increased? Like, will it increase or is it just?
No, decreases. The diffusion and holes across the current decreases. If the depletion.
No, the displacement current was the minority current.
Okay, that minority drift current, that is independent of the battery. Very, very small amount, negligible amount of current.
Okay.
So we are going to plot a VI characteristics of the potential difference current characteristics of a forward and reverse bias. Can you see the screen textbook?
Yes, ma'am.
See here, the first one, it is under the circuit is under forward biased. So the diode, it is connected to the positive terminal. N is connected to the negative terminal. See, a milliammeter is there. Milliammeter which measures the current in milliampere. A voltmeter is connected. We know the forward current is little more than the reverse current, isn't it? So this is the first circuit for forward biasing. See the reverse biasing, P is connected to the negative and N is connected to a positive, a voltmeter to measure the potential difference. A microammeter is the which measures the current in microampere. We are going to plot a graph. We are getting a graph like this. See, this one, note this is your forward biasing. So the current measured in milliampere. Here, this is microampere. So the current, this is the reverse biased. So can you understand now? See what happens when we connect the circuit in the forward bias. No current flows through the junction initially. We are increasing the voltage, but no current increase. So when the applied voltage, it is not greater than the barrier potential, no current, forward current is possible until this is represented by this region. We are going on increasing the potential difference, but there is no current. So when the forward bias becomes greater than the potential barrier, forward current starts increasing. That shows the linear portion start increasing linearly. So at a point, at a particular point, corresponding, this is at this point, can you see? It starts increasing the forward, it is like called as the knee point, knee voltage. So the current increases at rapidly above the knee voltage. This is shown here. Did you do this in the school?
Yes, ma'am.
So can you understand? Initially, you see go and see the graph afterwards. So this, and after some time, this part, and then it increases. This point is called as the threshold voltage, where the current increases more rapidly is called the threshold voltage. So you have to keep in mind, it is a forward biasing, it offers low resistance.
So we said that in forward bias, the depletion region was going down, right, ma'am?
Yeah.
So that means that
greater, no? Applied voltage, for example, if the applied voltage is very less, if the applied voltage is very small, the barrier potential will be slightly reduced. Only a very small amount of carriers will cross the junction. The current is very small and negligible. If we increase the voltage, if we increase the applied voltage significantly, the barrier height will be reduced. More number of carriers will be crossing the junction. The forward current increases. It depends on the applied voltage. Better to draw this now, mark the numbers also. See here, it will be This 0.2 volt. But the current measured in micrometer in the second case.
So at the threshold voltage, we can say the depletion region is 0, right?
Yes, very narrow. Not 0, narrow.
And for the reverse biased one, how is that increasing in there?
Yeah, let's see. Reverse biased. So this portion only I asked you to note. See, this is all 0, but here there is a leakage current. Did you note this leakage current in the class? Jana diode?
We noted that minority charge carrier would flow. The leakage current we've done as such, but Zener diode is out of syllabus.
Yeah, but did you do this practical means? Did you plot the graph like this? It should not be like this. A small leakage current, a very small leakage current, drift current should be there.
Yes, ma'am. We did the graph, but my graph came wrong thrice.
So after the class, you see, okay? So yes, very small current should be there. So what is happening here? So in the case of the minority carrier, we are increasing the reverse bias, keep increasing the voltage, the current increases. Current increases rapidly at a particular voltage. That is called the breakdown voltage. There it is called as the threshold voltage. Here it is breakdown voltage. Initially, we can see the drift current. It is independent of the voltage. And this, it is independent. Now, it rapidly increases and the current. So, this is the point of breakdown voltage, VBR.
Why does the current increase?
No, the breakdown voltage, it crosses the breakdown voltage. So if the breakdown voltage is this, after that the current increases rapidly. Until the breakdown,
what is happening at the breakdown voltage that is current to increase?
The minority carriers flow. The drift current is more.
So at the in reverse bias, we learned that it is creating somewhat of a battery of reverse potential, we can say.
Yes,
because of the depletion region.
We cannot use this. See, the reverse saturation current. For the diode in reverse, the current is very small and it is called the reverse saturation current. At very high reverse bias, the current suddenly increases. We are telling if you go beyond this, the current suddenly increases. The special action of the diode is Zener diode. We are not in this syllabus, it is not there. Okay. So the current first, in this case, current increases very slowly. And after a time, see, almost 0, then it starts increasing, then rapidly. But in this case, a small reverse current is there. And if we cross some value in that cutoff breakdown voltage, the current increases rapidly. Underline everything.
Yes, Pandya.
Now we are going to learn, the graph is clear, Nochet. Whatever point I told you, you can note down the milliampere, micro, this area, the small, everything. Now we are going to learn important term, dynamic resistance. What is the dynamic resistance? Dynamic resistance is ratio of small change in voltage to small change in current. This is small change in voltage divided by small change in current. The SI unit is, as usual, it is ohm. So from the graph, which increases linearly, we can only find the change in voltage to change in current. Okay. So in the textbook, if you are having a textbook with you, underline this, highlight this. Dynamic resistance.
But won't be connecting an emitter and all, no? So why can't we find normal resistance?
No, we can find it, but very, very small changes, no? See the graph. It's very small. If you plot only, we can see. This is dynamic resistance in the diode. It should be.
So dynamic resistance would be more like comparing, like it will be comparing resistance for like a whole area of graph, right?
Yeah. See, now read the question. We'll solve and I'll give one more question. Read this. The VI characteristics. Read it louder.
The VI characteristic of a silicon diode is shown in figure 14.17. Calculate resistance of the diode at ID
dynamic
equals 15,
current. Yeah. ID
equals 15 milliampere and VD equals minus 10 volt.
See, it is narrow. This is 15 milliampere. So we are taking two different points like this. Let us take this as V2, V1. And here it is, this is your I1, I2. This is your V1 and V2. What is the dynamic resistance? Change in voltage divided by change in current. What it is? It is in the voltage is 0.8 minus 0.7 divided by 20 milliampere minus 10 milliampere. Convert into ampere. Tell me the answer.
For the first one, I'm getting 10 ohm.
10 ohm, okay. Second one, it is 10 volt. It corresponds to 1 microampere. That's all.
How did we find the initial value here? Like they gave us ID at 15 milliamps.
They have asked the question, calculate the resistance of the diode at 10 volt. That's all. According to the question, they are answering.
No, I understood that, but then you said that we have to use like change in voltage upon change in current, right?
Yeah.
So here they have given only one value of the voltage. So what did we take the initial value as to find the change?
0.
Like over here you've taken 0.8 minus 0.7. So where did you get that?
Here we can take, if it is particular value, very small at the delta V tends to 0, like that we have to take at a particular instant. Very narrow. Minus 10 divided by?
For the second one, I'm getting, I'm not getting minus, I'm getting very high number.
The voltage is negative voltage, isn't it? Minus 10 divided by 1 microampere.
I got the power right. Should it be
10.
minus?
10, okay. The current will also be negative, no? So it will be only positive. Minus 10 divided by 1 into 10 raised to the power 6. So minus minus gets cancelled. 10 into 10 to the power 6 ohm. Correct. Okay, do this problem. The following, shall I dictate? Kiran, are you ready?
Just a second, I'm just writing it down.
Okay.
Yes, ma'am.
The following table provides a set of values. The following table provides a set of values of V and I obtained in a given diode. Take down the table. Forward biasing. Reverse biasing. V, I. 2 volt. 2.4 volt. This is a board question. 0 volt. 2 volt. 60 milliampere. 80 milliampere. 0 microampere, minus 0.25 microampere. Calculate the forward and reverse bias resistance of the given diode. Calculate the forward and reverse bias resistance. So how will you do the first one? Dynamic resistance, forward biasing.
I will just do 2.4 minus 2 upon 80 minus 60, but in the denominator we'll do 10 raised to the power 6.
Yes. Tell me the answer.
Uh, 2 into 10 raised to the power minus 8 ohm for forward.
So this is 2.4 minus 2 divided by 80 minus 60 milli then 10 power minus 3.
Oh, okay, sorry. So 10 power minus 5 then.
10 to the power
2 into 10 raised to the power minus 5.
It is, if I am taking there, it will be plus 3. So 0.4 into 10 raised to the power 3 divided by 20. What's the answer? 400 by 20, isn't it? 20 ohm. Where did you go wrong?
The power, man. Yes. I took off minus.
Okay. Do the next one carefully and tell me the answer.
I'm getting 4 into 10 raised to the power 6.
Power is correct. So it is
8, sorry, 8.
Okay, 8 means 8 into 10 raised to the power 6. So correct. Okay. So next two questions are board-based questions often asked. In the following diagrams, indicate which of the diodes are forward biased, and which are reverse biased. Take down the first one. See, if the positive is at high potential than the negative, for forward bias, P side should be at higher potential than the N side. So what is the P side here? 7 volt. N side is 5 volt. So it is forward biased because P side is higher potential than the N type. Right.
Yes.
Forward biased.
The P side is the triangle part in this, no?
Yes, yes. Higher potential 7 volt than the N side at 5 volt. Written.
Yes, sir.
Do this. It's grounded. Grounded means it is 0 volt. Now tell me.
This would be reverse bias.
Yes. Because the P side is lower potential, 0 volt, than the N side. Third one. Ground means it is 0 only.
This would also be reverse bias, no?
Yes, it is also reverse biased because P side is at higher potential minus 10 volt and this is at lower potential. Correct.
Ma'am, can you hear me?
Yeah, now I'm here.
I got disconnected.
Now do this.
This is also reverse bias.
Can you hear me? Yeah, tell me. What is this? Reverse or forward biased?
The reverse, ma'am.
Why?
Oh no, sorry, the minus.
Minus, yeah. So it is higher potential. P is at higher potential and N is at lower potential. Then it is forward biased. Shall I go to the
You're drawing a new one, no?
No, I'm just determine the currents through the resistance. Determine the currents through the resistances of the circuits shown below. The first circuit. Tell me. Both the diodes D1 and D2 are forward biased, isn't it? So what will be the current in the circuit? I equal to, here it is given directly 2 by 2 by R, 2 by 20, 0.1 ampere.
We don't have to consider the resistance which will be offered by the semiconductor.
Yeah. Yes, it allows the unidirectional flow of current. This is to show that flow of current in the diode is unidirectional. The forward bias, it offers infinite resistance. These things. It is the current across the 20 ohm resistor. Even. Tell me. D2 is reverse biased, isn't it?
Yes, ma'am.
Then what will be the current?
But D2 shouldn't let current pass through.
Yeah, pass through. So the current should be 0.
Yes, ma'am. It will be 0 for D1 also, right, ma'am?
Yeah, the current, yeah, it will block here. No? So I will be equal to 0. So in this case, what will be the answer for in this case? Kiran, are you answering? I can't hear you.
Yes, ma'am. I'm just doing it. Current through D1 and D2 respectively will be
Same.
20 ampere, ma'am.
Yeah, not 20.
And
current. No, same current. No, it offers zero resistance. That's what we want. What is the current through this? Both will be same. It offers zero resistance. It's not offering any resistance to the circuit. So same thing. I equal to 2 by 20. 0.1. If the current is flowing, it is offering no resistance at all.
That will be I net, right? Oh, we can't calculate it individually.
Yes. Current
we can't calculate individually for the semiconductor.
Current in the circuit. Read the question. Current in the circuit.
Yes, sir.
Only last one.
Current would be half of the...
No, fully only. The way is blocked. Imagine as there is no D2 at all. Okay, the way is blocked. The current will be, I will be only 20 by 2. 2 by 20. This portion is not here. That's all.
Okay.
See what in general what we saw today allows the diode allows only the unidirectional flow during forward bias. Reverse saturation current is very low. The forward bias resistance is lower than the reverse bias resistance. And we learned an important topic term dynamic resistance. Is it clear? So I just give the introduction about the rectifier. In the next class, we are going to see half wave and full wave rectifier. Then we have a very small portion in this lesson to complete it, the photodiode, LEDs, solar cell. Okay. Then we have 1 or 2 classes we need for nuclear. What is a rectifier? Have you seen in the mobile charger or in your laptop charger, somewhat it will be 20 volt DC, 12 volt DC, 4 volt DC. What is this? We have to charge this at 20 volt. That too, for in our house, it is AC supply. It should be converted to DC. There are some situations we have to convert AC into DC. And we have to bring down the voltage also. Where we have learned to bring down the voltage, step down transformers. And this is converting AC to DC. We are going to see what is a rectifier, how it is going to help us. Is it clear? So when is our next class? Thursday. Thursday we will continue. Okay, check. Thank you.
Yes. Thank you, ma'am.
Good evening. Thank you.